Hi, everyone, and welcome to this next installment in my pre-calculus and algebra video series. In this video, we're going to talk about the double angle formulas, the power-reducing formulas, and the half-angle formulas. Now, it may sound like a lot, but as we go through these, you'll see that it's really just the same thing, tweaked slightly and talked about in two different ways. So it's not really three different topics. It's really just sort of one collective group of formulas. Now, I'm going to work through, as always, a handful of problems. I think I'm going to do 5 problems in this video. So if you want to just take a look, pause for a moment. These are the 5 problems I'm going to be doing later. But before we get into them, let's talk about some of these formulas. So I'm going to start with the double angle formula. So double and then power reducing and then half angle. So double angle formulas first. Well, to talk about the double angle formulas, I'm going to go back to the previous video, the one right before this one, where I talked about the sum and difference formulas. Right? This was the topic of the last video. I don't need all 6 of them. There's a plus and a minus for cosine, a plus and a minus for sine, a plus and minus for tangent. I don't need all 6. I'm just going to use the sums, right? So let's we don't need this guy right now. We don't need this guy right now. We don't need this. Let's see. We don't need this guy right now, right? So let's just keep the ones that have a plus. All right. So that's what I have here. Call them the sum formulas. There's just the sum formulas. Okay, so alpha and beta can be any angle. Can be any angle. At least any angle for the cosine function and the sine function. They can't be any angle for the tangent. They could be any angles that don't give you undefined. So let's say any angle in the domain of each function. Any angle in the domain. So remember, tangent is not defined for all real numbers because sometimes you get a 0 on the bottom of the fraction. Tangent is sine over cosine. So anywhere the cosine is 0, tangent's undefined. But let's just say in the domain of each one of these functions, alpha, right? There's alpha and beta. There's beta. Alpha and beta could be anything. So what happens when they're the same number? When they're both, let's say, pi over 6, or they're both 105 degrees, but they're the same number. Well, let's see. Let's start with the sine function. If alpha and beta are the same, then we get the sine of alpha plus alpha, right? Alpha and beta are interchangeable, so I'll replace this beta right here. I'll just call that alpha because they're the same. So the sine of alpha plus alpha. And according to this formula, again, this is a formula from the last video, the sum and difference formulas. According to this formula, it's the sine of the first angle times the cosine of the second angle, which is also alpha, plus the cosine of the first angle, alpha, times the sine of the second angle, which is also alpha. Everything's alpha. Right? So each of these terms, this one and this one, is a sine times a cosine. Right? The first one's sine times cosine, the second one's cosine times sine. Order doesn't matter. Right? Order doesn't matter. So we get the sine of alpha plus alpha, which is 2 alpha, is equal to 2 times the sine of alpha times the cosine of alpha. And this is the double angle formula for sine. Right? So it's really just a special case of the sum formula. When the two angles are the same, you get this. Right? And this is the first double angle formula, the double angle formula for sine. Same thing works for tangent and cosine, cosine and tangent. I'm going to do tangent second, and I'll do cosine third, right? We don't have to do things always in the same order. So if, again, alpha and beta are the same, that becomes tangent of alpha plus alpha is equal to the tangent of alpha plus the tangent of alpha divided by 1 minus the tangent of alpha times the tangent of alpha. Just replace the beta with the alpha, right? Two angles are the same. So we get the tangent of 2 alpha is equal to, well, on top, we've got tangent alpha plus tangent alpha. So we've got 2 of those guys, 2 times the tangent of alpha. And on the bottom, let's see, 1 minus tangent of alpha times itself. So that's going to be tangent squared of alpha. And there is our double angle formula for tangent, right? We just take the sum formula that has an alpha and a beta. Say, okay, let's say those two numbers are the same. Alpha is equal to beta. So here's our double angle formula for tangent. And then same exact thing for the cosine. Cosine of alpha plus alpha is equal to the cosine of the first angle times the cosine of the second angle, which is the same, also alpha, minus the sine of the first angle, which is alpha, times the sine of the second angle, which is also alpha. So we get the cosine of 2 alpha is equal to cosine times cosine is cosine squared. Sine times sine is sine squared. All right. So there is our double angle formula for cosine. So let me just go back over the last couple of slides. We've got double angle formula for sine. We've got double angle formula for tangent. And we've got double angle formula for cosine. Don't worry, I'm going to put all these formulas together on one slide to make it nice and easy to reference. The reason I did cosine last, I did the sine first, then the tangent, then the cosine, is because there's a couple other ways we could state this. Anytime you see these squares, either sine squared or cosine squared or secant squared or cotangent squared, and you see a square of a trig function, you think, Pythagorean identity. Right? Sine squared plus cosine squared equals 1. Right? It doesn't necessarily apply, but it might. There's a high likelihood that it applies. So let's stick with this double angle formula for cosine. On the next slide, I've got it written twice. So this is just from the previous slide. Cosine of 2 alpha equals cosine squared minus sine squared. And again, I just have it written twice. And the reason I have it written twice is because if we take our original Pythagorean identity, remember there's 9 of these. There's 9 Pythagorean identities. 3 of them for sine and cosine. Okay, so sine squared plus cosine squared equals 1. And then if we subtract cosine squared from both sides, we get this one. If we subtract sine squared from both sides, we get this one. So these are the 3, the 3 statements of the Pythagorean identity for sine and cosine. Well, sine squared is equal to 1 minus cosine squared. Okay, so let's use that one. We got a sine squared right here, sine squared of alpha. And that is the same as 1 minus cosine squared of alpha. Let's get rid of all this red. Let's just use green. Okay, so sine squared is 1 minus cosine squared. So let's make that substitution. And we will get the cosine of 2 alpha. Remember, this is the double angle formula, is equal to cosine squared of alpha minus, well, in green, we can replace that with 1 minus cosine squared of alpha. And if we distribute that negative sign, minus the 1 and minus the cosine squared, we get cosine squared minus 1, and then cosine squared minus a minus cosine squared, so that's plus. So that will give us 2 cosine squared. Yeah, I'll just write it all out. It just doesn't take too much extra time. So that'll be cosine squared alpha minus 1 plus cosine squared alpha. So the cosine of 2 alpha, we've got 2 of these cosine squares, cosine squared of alpha minus 1. So this is an alternate version of the double angle formula. For cosine. And we could have just as easily used this other, oh, I meant to use a highlighter there. We could have just as easily used this other version of the Pythagorean identity, where cosine squared is 1 minus sine squared. So yellow to yellow. That yellow cosine squared alpha, we could replace that with a 1 minus sine squared of alpha. So cosine of 2 alpha is equal to 1 minus sine squared of alpha. Right, that's the yellow part. And there's minus another sine squared of alpha. So we get the cosine of 2 alpha is equal to 1 minus 2. Nope, I'm saying sine, but I'm writing cosine. 2 sine squared of alpha. And that is another alternate. So we got 2 alternate versions of the double angle formula for cosine. All right. So let's just put these all together so we have them all on one nice list on the next slide. All right, so we've got the double angle formula for sine. We've got 3 different double angle formulas for cosine, and we've got the double angle formula for tangents. Okay. So let's do a couple of problems. Use the figure to the right, this guy right here, this triangle, right? We got 2 angles labeled. There's an alpha and a beta. Now remember, if we're talking about trig functions and right triangles, we got to talk about opposite sides, adjacent sides, and hypotenuses, right? This side right here is the hypotenuse. the longest side, which is opposite the largest angle, right? But the other two sides, one of them's opposite and one's adjacent, but you have to be careful. If this is your angle, and if you're working with that angle right there, alpha, then this side is opposite and this side is adjacent. All right, so look at part A, cosine of 2 alpha. Look at part B, sine of 2 alpha, right? 8 is the opposite side, 6 is the adjacent side. But then in part C, we're talking about tangent of 2 beta. So if that's our angle, well, then this becomes the adjacent side. And this becomes the opposite side. So we just have to make sure we're careful with what we label as opposite and what we label as adjacent. Hypotenuse is always the longest side opposite the 90-degree angle. Okay, so we'll do B and C later. Let's look at part A. What is the cosine of 2 times alpha? Well, let's just start with our definition. What is the definition of the cosine function? Well, cosine of an angle. I'll use theta. I'll use a different angle here. It doesn't matter. Use whatever letter we want. Cosine of an angle is equal to the length of the adjacent side divided by the length of the hypotenuse. Right? So if our angle is alpha, right, for this triangle, the adjacent side is 8. And the hypotenuse is, well, we don't know. What is the hypotenuse? We know the two legs of this triangle are 6 and 8. But what is the hypotenuse? So we definitely want to, if you're using a right triangle, you want to make sure you know all 3 sides. And to figure out that missing length, we can use the Pythagorean theorem. A squared plus b squared is equal to c squared, where c is the hypotenuse. So 6 squared plus 8 squared equals c squared. 6 squared is 36. 8 squared is 64. Right, so c squared is equal to 36 plus 64, which is 100. So c is equal to 10. Right, so the length of the hypotenuse is 10. So the 3 sides of this triangle are 6, 8, and 10. So that means that the cosine of alpha is 8 over 10, which is 4 over 5. Adjacent over hypotenuse. Oh, sorry. I'm saying one thing and I'm writing another. Adjacent is the 6. Whew. It must be late. It's late right now. Adjacent is 6. So that's 6 over 10, which is 3 over 5. Okay, we got to be careful here. Cosine of theta, or cosine of alpha is 3 over 5. Now, we're not looking for cosine of alpha. We're looking for cosine of 2 alpha. Right, so the cosine of 2 alpha is equal to, now let me go back to the previous slide. We've got this one, we've got this one, and we've got this one. I think these two are easier to work with because they only contain one trig function, right? The one in the middle contains only cosine. The one on the bottom contains only sine. The one on the top contains both. Now each trig function is going to be a fraction. So the one on top contains 2 fractions. The other 2 contain only 1 fraction. So let's use one of those two. So I'll say 2 cosine squared alpha minus 1. Right, we could write that as 2 times the cosine of alpha squared minus 1. And if the cosine of alpha is adjacent over hypotenuse, which is 6 over 10, which reduces to 3 over 5, well, that's right here, cosine of alpha, 3 over 5. So that becomes 2 times cosine of alpha, which is 3 over 5. It's still squared. We got to do the square. Minus 1. All right, so that's 2. 3 times 3 is 9. 5 times 5 is 25. And we've got a minus 1. So that will be, let's see, 2 times 9 is 18 over 25 minus 1, or 18 over 25 minus 25 over 25. I'm showing every step here. So that will be negative 7 over 25. All right, cosine of 2 alpha. So we'll do the same thing with the sine of 2 alpha and the tangent of 2 beta. Right? We've already figured out that this side is 10. We have a formula. So now we're on part B. The sine of 2 times an angle is equal to 2 times the sine of the angle times the cosine of the angle. 2 times the sine times the cosine. Well, definition, the sine of an angle is equal to the length of the opposite side, which is 8, divided by the length of the hypotenuse, which is 10. So the sine function connects those three. The sine function connects those three, that angle and those two sides. So opposite over hypotenuse, reduce the fraction, we get 4 over 5. And we already saw on the previous slide, the cosine of alpha is the adjacent over the hypotenuse, which is 6 over 10, which reduces to 3 over 5. Right? Sine of alpha is right there. Cosine of alpha is right there. All right, so this shouldn't be too bad. The sine of 2 alpha is, let's go back to blue, is equal to 2 times the sine of alpha, which is 4/5, times the cosine of alpha, which is 3/5. All right, so we've basically got 2 over 1 times 4 over 5 times 3 over 5, multiply across the top. 2 times 4 is 8. 8 times 3 is 24. Multiply across the bottom. 1 times 5 is 25, and we can't reduce that. So that is the sine of 2 alpha for this triangle, this 6, 8, 10 right triangle. All right, looking good. So now we've done the cosine, we've done the sine. Let's do the tangent of 2 beta. Tangent of 2 beta. Now remember, this is beta, so this becomes the opposite side. And this, let me see if I could write vertically. That's the adjacent side. And so the tangent of beta, we need tangent of 2 beta, but we'll start with this one. Tangent of beta is equal to the opposite side, length of the opposite side, divided by the length of the adjacent side. Opposite side is 6, adjacent side is 8, and that reduces to 3/4. Okay, looking good. We got a formula for the tangent of 2 beta. Tangent of 2 times an angle. In this case, where the angle is beta. So tangent of 2 beta is equal to 2 times the tangent of beta divided by 1 minus tangent squared of beta. And we could write that as 2 tangent of beta. You don't have to do this, but it just makes it more sort of visually in line with what's actually happening. 1 minus the tangent of beta squared. Right, this and this, they mean the same thing. And the reason I write it like this is because we're substituting for tangent of beta, not tangent of beta squared. Right, so the tangent of beta is 3/4, and so we've got a tangent of beta here. We've got a tangent of beta here, so they both become 3/4. Okay, so let's see, this becomes 2 times the tangent of beta, or 2 times 3/4, all divided by 1 minus 3/4 squared. All right, let's see, let's bring it over here. So just so we make sure we have enough room. 2 times 3/4, that's 6/4, or 3/2. Okay. On the bottom, we've got 1 minus 3/4 times 3/4. So that'll be 9/16. So we've got 3. Yeah, so what's driving us right now? Like what are we trying to do? Just so we know, why we're doing what we're doing. Well, I'm thinking if we have one fraction divided by one fraction, then we could rewrite that as multiplication. Right, so it'll be A over B times D over C. Keep, change, flip. All right, so that's sort of the direction I'm going right now. I want one fraction on top, which I got, and I want one fraction on the bottom, so I got to combine those two. Got to combine those two. Okay. Now back to the problem. We've got 3/2 on top. 16/16 minus 9/16. So now we've got one fraction on top, and we've got one fraction on the bottom. That's what we want. So now we could rewrite this as the multiplication of two fractions. So that'll be 3/2. I said 2 times 16/7. The 16 and the 2 cancel to an 8 and a 1. All right, 16/2 is the same as 8/1, so we could do that. Or you could simplify at the end, doesn't matter. I think it's simple. It's easier to simplify first. Then you're bringing the numbers down instead of letting them get big. 3 times 8 is 24. 1 times 7 is 7. And that should do it. 24/7. All right, so number one, well, it was actually 3 problems. Cosine of 2 alpha, sine of 2 alpha, tangent of 2 beta. All right, looking good, looking good. Let's do one more. Similar problem, still sticking with the triangles. So let's say, given that sine of theta is negative 15/17, and theta lies in quadrant 3, find the exact value of cosine of 2 theta, and then sine of 2 theta, tangent of 2 theta. So we'll deal with these two afterwards, after we're done with the cosine of 2 theta. So let's start with the cosine of 2 theta. So let's do the same thing. Well, actually, we're missing one little piece of information. It's that triangle. Okay, so we've got a right triangle. And by definition, right, if the sine of the angle theta, so we have to label theta somewhere, right? It doesn't matter. Wherever you want to put it, you can't put it at the right angle, that's 90, but you can put the theta there. You can put the theta there. Makes no difference. I tend to always put the theta at the bottom. Either way, if the sine of theta is 15/17, we'll ignore the negative sign for now. We'll deal with the negative sign later. I'm just looking at the lengths of sides. Negative just means it's going in the negative direction, either to the left or down. So sine is opposite, right? Opposite is 15 over hypotenuse, right? So there is our triangle. As soon as you see this, sine of theta is negative 15/17. That's telling you in a right triangle, the side opposite theta is 15 and the hypotenuse is 17. So we got to figure out that other side. A squared plus b squared is always equal to c squared for right triangles. And a and b are these two sides, a and b, right? C is always the hypotenuse. So we could say 15 squared plus b squared is equal to 17 squared, right? 15 squared is 225 plus b squared. And 17 squared is 289. You could double check this on a calculator if you don't believe me, right? Subtract 225 from both sides. We'll get b squared is equal to 64. And if we take the square root of both sides, we only want the positive, of course, because we're looking at length. B is equal to 8. All right, so now we've got our triangle. 8, 15, and 17 are the 3 sides. So now it's very similar to problem number 1. So let's go through this a little bit quicker, just because we already did it. The cosine of 2 theta is equal to 2 cosine squared theta minus 1. which is equal to 2 times, well, what's the cosine of theta? Cosine is adjacent over hypotenuse. Right, so it's cosine would be adjacent cosine of theta, right? So adjacent is 8, hypotenuse is 17, and that's squared minus a 1. All right, let's see. We've got 2 over 1. That's 2. 8 over 17 squared. Well, 8 times 8 is 64. 17 times 17, that's 289. Minus 1. Well, let's get a common denominator. So let's say that's 289 over 289. Make sure that looks like a 2, an 8, and a 9. Okay. So that's 128 minus 289 all over 289. And I think 128 minus 289, you may want to double check this, but I'm pretty sure this is right. Negative 161 over 289. All right. So that is the cosine of 2 theta. But wait a second. Do we keep the negative sign or do we make it positive? So now we have to worry about the signs. Now we have to worry about the pluses and the minuses. Right? In quadrant 3, down here in quadrant 3, this is quadrant 1, this is quadrant 2, quadrant 3, and quadrant 4. So in quadrant 3, the sign is negative because the y values are negative, but also the cosine is negative because the x values are also negative. So yes, we'll keep the negative sign, negative 161 over 289. So this determination of whether to use the negative or keep the negative or drop the negative, it all has to do with quadrants, quadrant 1, 2, 3, or 4. Sine and cosine are both positive in quadrant 1. They're both negative in quadrant 3. In quadrant 2, the sine is positive, cosine negative. In quadrant 4, sine negative, cosine positive. Okay, looking good. Next one, sine of 2 theta. Well, we're working with the same right triangle, right? 8, 15, and 17. The sine of theta opposite over hypotenuse. The cosine of theta adjacent over hypotenuse. So the sine of 2 theta, we're going to go back to our formula, our double angle formula that we previously just established. The sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. Which is 2 times the sine of theta. It's coming from over here. Sine of theta is 15 over 17. The cosine of theta, 8 over 17. We can put that 2 over 1. So now we got 3 fractions. Top times top times top. 2 times 15 is 30. 30 times 8 is 240. On the bottom, 1 times 17 times 17. Well, that's going to be 289. All right, so sine of 2 theta, it's going to be 240 divided by 289. Now we've got the last one, the tangent of 2 theta. Again, same triangle. This angle is 90. This one I'm calling theta. Hypotenuse is 17. The other 2 legs were the 8 and the 15. So 8, 15, angle. And I don't think we're going to need it for this one, but we saw that the sine of theta is opposite over hypotenuse. The cosine of theta is adjacent over hypotenuse, 8 over 17. And then the tangent of theta is opposite over adjacent. Opposite, adjacent, hypotenuse. Okay, so these are the 3 primary trig functions. Now, the tangent of 2 theta. Well, according to our double angle formula, that's 2 times the tangent of theta, all divided by 1 minus tangent squared of theta. And again, this next step is, I tend to write it when I'm explaining. It's not necessary to write it out, but just rewriting the square using parentheses, just because I think it's more visually apparent what's actually happening in the problem. We've got a tangent of theta, we've got a tangent of theta, and we've got a tangent of theta over here. So you could replace tan theta with 15 over 8. Right, so that'd be 2 times 15 over 8 on top, and we've got 1 minus tangent of theta squared, so 15 over 8 squared. All right, so let's see. On top, we've got 2 times 15 over 8, that's 30 over 8, or 15 over 4. I got fractions inside of fractions right now, so again, I'm thinking, just like in the previous couple problems back, fraction over fraction. You want to rewrite this using multiplication. All right, so that's where my mind is right here. I'm seeing fractions over fractions, so I want to try to combine all of the terms into 1 on top, all of the terms into 1 on the bottom. All right, so 15 over 4 on top. We've got 1 minus, well, we got to square this. 15 squared, so 15 times 15 is 225. 8 times 8 is 64. Okay, so that becomes 15 over 4 on top. Let's get a common denominator, so 64 over 64 minus 225 over 64. So that's 15 over 4, all divided by, let's see, 64 minus 225, I think that would be negative 161 over 64. We're almost there. So now keep, change, and flip. Instead of 161 over 64, we'll take the reciprocal. 64 over 161. We could do a little bit of canceling. 4 goes into 64. I think that's 16 times. We got 15 times 16 on top, negative. So we've got negative. That should be 240. And we've got 161 on the bottom. And does that reduce? No. That's as far as we go. Tangent of 2 theta, negative 240 over 161. Now, you may be thinking that took forever to do 2 problems. We actually did 6. All right, so we just knocked out 6 problems, 6 double angle formula problems. So I think that's practice enough. I think we're ready to move on. To the power reducing formulas. No, you know what? I think I've got, if my memory serves right, I think I've got one more problem on deck. And yeah, that's right. One more problem. This one's not bad. This one's a short one. Right? Maybe it looks complicated, but it's really like once you see it, it won't be too bad. Well, first, let me just copy down the formula for the tangent of 2 theta. That's 2 times the tangent of theta divided by 1 minus tangent squared theta. All right, so it's all, the directions say, write the expression as the sine, cosine, or tangent of a double angle, right? So we're basically of a double angle. So we definitely want to look at the double angle formula, and this is the double angle formula for tangents. Tangent of 2 theta is 2 times the tangent of theta divided by 1 minus tangent squared theta. Well, what is theta in this problem? Right, look at this. I mean, this right here looks like this right here. So you've got 2 times the tangent of 7 pi over 8 divided by 1 minus the tangent squared of 7 pi over 8. That means 7 pi over 8 is our theta. That's our angle for this problem. Theta is 7 pi over 8. Okay, well, what do we got on the left-hand side of the equation? We've got the tangent of 2 times theta. So 2 times 7 pi over 8. Well, let's look at this guy on the left. All right, let's look at this guy right here. What is that? What is that equal to? Well, it's actually equal to -1. It's actually equal to -1. So 2 times 7 pi over 8, well, the 2 and the 8 cancel. That becomes a 1 and a 4. So that becomes the tangent of 7 pi over 4. And the tangent of 7 pi over 4 is -1. Tangent of 7 pi over 4 is -1. So there's our answer. Right? If you think about the unit circle, pi over 4, 2 pi over 4, 3 pi over 4, 4 over 4, 5 over 4, 6 over 4, 7 pi over 4 is over here. Terminal point is positive root 2 over 2, comma negative root 2 over 2. That's our terminal point for an angle of 7 pi over 4. Tangent is y over x. So I guess we could just put in one step before the -1 if you want. That's equal to -√2/2 divided by positive √2/2, which is equal to -1. Okay, so I think that's enough for the double angle formulas. The next or the rest of this video, I want to talk about the power reducing formulas and then the half angle formulas. I'm actually going to stop this video now. We'll break this up into part 1, part 2. This will be part 1, the double angle formulas. As soon as part 2 starts up, it'll pick up right where this one left off at the power reducing and half angle formulas. All right, that's it for now. I hope this was helpful.